In this video, I will show you how to write and graph the standard form equation of a hyperbola. And for now, we will leave the center at 0, 0. Here are the graphs of two hyperbolas. We're going to compare and contrast with what we know about ellipses. So notice that a hyperbola has two branches. We will consider this to be a horizontal hyperbola when it opens to the left and to the right. And we will consider it to be a vertical hyperbola when it opens up and down like this. Now, let's compare a few things with an ellipse. Let's start by looking at the equation that we learned when we learned about ellipses. Notice how we have a fraction plus a fraction is equal to the number 1. When we look at the standard form equation for a hyperbola, we have the fraction minus the fraction equals the number 1. So it's almost the same as for an ellipse, but with a minus instead of a plus. Now, let's talk about A, B, and C. Just like for an ellipse has a vertex. It has two vertices on either end. And the A value was always the distance from the center to a vertex. Similarly, when we look at a hyperbola, the center is not, the center is going to be halfway between the vertices. But the distance from the center to a vertex is still A. Now, looking back at an ellipse, if we looked at the distance from a center to a covertex, that was a B value. Now, looking at the hyperbola, we've got this B value. Now, the distance from the center to a covertex is still the B value. The only difference is a covertex is not actually on the hyperbola. It helps us form this rectangle that we use to see where the asymptotes are. So that's another thing that is new. A hyperbola is the only conic section that has asymptotes. And the A value and the B value form this rectangle, and the diagonals of the rectangle show you where the asymptotes will be. Now let's talk about the C value. When we learned about ellipses, it turned out that the C value was the distance from the center to something called a focus. Center to a focus. That was the C value. That's going to be the same for a hyperbola. A hyperbola has two foci or foci like this, and the distance from the center to a focus will be the C value, just like it was for an ellipse. Now, let's talk about what is different. When you were dealing with an ellipse, whenever we talked about A squared or the A value, A squared was always bigger than B squared. A was always bigger than B. That is not going to be true for a hyperbola. Sometimes the B squared value will be bigger than the A squared value. So how do you know which one is going to be A squared and which one is going to be B squared if we're not going to go by the one that's bigger? Well, the way it works for hyperbolas is, because of this minus that you're going to have, you're always going to have one positive term and one negative term. The positive term is always going to have a denominator of A squared, and we will always put the positive term in the front. The negative term will always have a denominator of B squared, regardless of whether it's bigger or smaller. And the negative term always goes second. So notice that whereas for ellipses, we always put the x term first, no matter what. The x term was always first. For hyperbolas, the positive term is always first. Sometimes that'll be the x term, sometimes it'll be the y term. And that is what determines whether or not the hyperbola will open horizontally or vertically. If the positive term is the x term, then the hyperbola will open in the x direction, horizontally. If the positive term is the y term, it will open vertically. Now, in standard form, the positive term is always first. So I could say if the first term is the x term, it's going to open horizontally, left and right. If the first term is the y term, it will open vertically, up and down. Here's some additional vocabulary. All right, the center is going to work the same as it did for ellipses. All right, the center is still the opposite of this and the opposite of this, h comma k. There's something called the transverse axis, which is the segment connecting the two vertices. So let me just highlight that real quick. This would be the transverse axis. All right, so this is a horizontal transverse axis, again, when the x term is first. And this would be the transverse axis for this hyperbola, a vertical transverse axis. Okay, that's the transverse axis. If I drew the line segment that goes from covertex to covertex, that's called the conjugate axis. So this is the conjugate axis, and this is the conjugate axis. Okay, I think we talked about all of this. Oh yeah, one more thing. When we were dealing with ellipses, the equation relating a, b, and c was c squared is equal to a squared minus b squared. For hyperbolas, the equation is now c squared is equal to a squared plus b squared. So that's different, so be careful. Let's do an example. We are given the standard form equation of a hyperbola. Notice the minus sign. We need to find all these values and graph the hyperbola. So remember that for a hyperbola, the a squared value is always first. It's the positive term denominator. So a squared is 16. That means a is going to equal 4. Now, this will give me my vertices. So let's go ahead and deal with that right now. Oh, also the center. Since we just have x squared and y squared, the center has to be 0, 0. Okay, otherwise there'd be parentheses and something would be subtracted or added inside there. So if you ever just see x squared and y squared, you know that it's 0, 0. So this a value is always going to give us the vertices. Okay, because the 16 is with the y term, when I do this plus and minus 4, I'm going to do it in the y direction. So let's go ahead and reinforce the fact that here's my center at 0, 0. Now here comes my a value, positive 4. I'm going to go up 4 and down 4. So these are my vertices. Okay, and I already know that my parabola will be opening up and it will be opening down. So my vertices are 0, 4 and 0, -4. Okay, how about the covertices? So the second one, the denominator of the negative term, is going to be b squared. So I know that b squared is 9. That means b is 3. Because the 9 is in the x term, I'm going to do plus or minus 3 in the x direction. So starting from the center, I will go left 3 and right 3. So these are my covertices, even though they will not actually be on the hyperbola at all. So -3, 0 and 3, 0. Now, the vertices and the covertices will form a rectangle. And let's draw that rectangle as a dotted line, like this. Okay, that rectangle is going to be really important because the diagonals of this rectangle will show me where the asymptotes are. So I'm going to sort of keep track of the slope here from the center to the corner. This is up 4 and over 3. I'm going to keep track of that because if I want to put another point down, I would need to again go up 4 and over 3. And that will help me keep my asymptote more accurate. Okay, so I will do the same thing in the other direction. Okay, in this direction I'm going down 4 and left 3. So that would be like here. Okay, so that is one of my asymptotes, and I will do the same thing right here. All right. Okay, so I've got the asymptotes. Now, remember that these red dots were my vertices. So we knew right from the beginning that this was going to be opening up and down. But when you draw these branches, they should be approaching the asymptotes on the left and the right. Okay? And same thing down here. Approaching the asymptotes. Okay, so that is a pretty good sketch. But now we need the foci, which will be somewhere in the interior of each branch. To get the foci, we're going to need the C value. So remember the equation relating A, B, and C. For hyperbolas, that equation becomes C squared is equal to A squared plus B squared. So C squared is going to equal 16 plus 9. So C squared is equal to 25. So C, well, I'll just write it here. C is 5. So that is going to tell me where the foci will go. So from the center to the focus is 5. So if I go up 5, here will be a focus. All right, and here is a focus if I go down 5. All right, so that is 0, -5 and 0, +5. Now, the eccentricity does not change. For ellipses, the eccentricity was C over A. That's still going to be the same for hyperbolas. So it's still going to be C over A, 5 over 4. Okay, notice that this is bigger than 1. For hyperbolas, the eccentricity is always bigger than 1. All right, for ellipses, it was always less than 1. All right, let's jump over to example B. Now, right from the beginning, you should be able to decide which of the following will be true. Is this going to be a hyperbola with a horizontal transverse axis opening to the left and right? Or will this be a hyperbola with a vertical transverse axis opening up and down? You should know this at a glance. Notice how the first term, the positive term, is the x term. That's how we know that this will be a horizontal transverse axis, opening left and right. So whatever else we do, in the end, make sure your branches open to the left and to the right. The center is still 0, 0, because it's just x squared and y squared. So here's my center once again. Let us find the vertices by using the a value. A squared is always going to be the denominator of the positive term, which will be first. So a squared is 49, which means a is 7. So I'm going to do plus or minus 7. Because the 49 is in the x term, I'm going to do my plus or minus 7 in the x direction. All right, so I'm going to go 7 to the right and 7 to the left. These are my vertices. So negative 7 comma 0 and 7 comma 0. So remember, the red ones are my vertices. So now let's do the co-vertices in purple. The b squared value is always going to be the second one, the denominator of the negative term. So the b value is going to be 4. This 4 will lead me to the co-vertices. Since the 16 is with the y term, I will do plus and minus 4 in the y direction. So starting from the center, I will go up 4 and down 4, and these are my co-vertices, 0 comma negative 4 and 0 comma positive 4. Those are my co-vertices. Okay, the vertices and the co-vertices define a rectangle. So I'm going to draw a rectangle where the sides contain the vertices and the co-vertices. All right, draw your rectangle as a dotted line like I'm doing. Okay, the diagonals of your rectangle are going to be the asymptotes of the hyperbola. Okay, so I can really draw my hyperbola right now. Remember, these red dots were the vertices, so these are the only points that are actually on the hyperbola. So I will start here, and I will approach the asymptotes. Okay, and then similarly over here, I will approach the asymptote. Okay, and there you go. The co-vertices, again, are not on the hyperbola. So all I need now are the foci. Not sure why they're not asking me for the equations of the asymptotes. I feel like that should be on here. I'm going to add that in. Okay, so anyway, the foci, we will need the c value. Okay, so we know that c squared is equal to a squared plus b squared for hyperbolas, not minus like it is for ellipses. So c squared is equal to 49 plus 16. So c squared is equal to, c squared is equal to 65. Taking the square root of both sides, c is equal to the square root of 65. Okay, and this does not simplify our lunch today. So I'll just put the square root of 65. This is approximately equal to 8.5 8.1. I'm just going to use this for graphing purposes. Okay, so 8.1. So this is 7, 8. So I'll have a focus here, and I'll have a focus over here. Now, I cannot use the 8.1 when I label the foci. I have to use the radical 65. Okay, so be careful. I know that the y value of this focus is going to be 0. It's going to be something comma 0. All right, this is on the x-axis, so I know the y-coordinate is 0. So it's just a matter of what's the x-coordinate. Well, start from the center, and I'm going to the right radical 65. So that means the x-coordinate here is radical 65. So this is going to be negative radical 65, comma 0. So those are the coordinates of the foci. Negative radical 65, comma 0, and radical 65, comma 0. The eccentricity is still c over a, so that'll be radical 65 over 7. Now I'm going to add something on here. The asymptotes. We need to know what the equation of, well, the equations, plural, of these two asymptotes are. All right, so let's see, asymptotes. Okay, and the way I write the asymptotes is I use the point slope form of the equation of a line. So point slope form works like this. If I have a point that's on the line and a slope, my equation will be y minus y1 is equal to m, that's the slope, times x minus x1. Now, m is the slope. The x1 and y1, those are the coordinates of a point on the line. So, for the slope, I can just look at this. What's the rise and what is the run? This is up 4 and over 7. So when I write my equation in a moment, I'm going to have 4 over 7 where the m goes. Okay, so now I'm going to have x and I'm going to have y. Now, inside of these two positions, I need the coordinates of a point. And I will do the opposite of those coordinates. Well, there's one point that's on both asymptotes, so I should definitely use it, and that's the center. Since the center is 0, comma 0, I'm going to put 0 for x1 and y1. So that means I'm really done. In fact, since this is just 0, I don't even really need these parentheses, do I? Okay, so I have y equals 4/7 x. The only thing is, this is the equation of the upward sloping line. What about the downward sloping line? Well, I used the same point, so the only thing that's changing is the slope, which is down 4, right 7. So instead of positive 4 over 7, it would become a negative 4 over 7. So I can do a shortcut and represent both lines by putting plus and minus. So this means the equation of the upward sloping asymptote is y equals positive 4 over 7x, while the equation of the downward sloping asymptote is y equals negative 4 over 7x. So just put plus or minus and you've got them both. Okay, I did not write the asymptotes for example A. So I'm going to go ahead and do that now. Let's just add that in. Okay, asymptotes. Okay, so look, the center is 0, 0 again. So again, I will just have y, and I will have x. Okay, nothing added or subtracted because of the zeros. All I need is the slope, and it will be plus or minus because one is going upward and one is going downward. So what is the slope? Well, it's up 4 over 3 for this problem. So I will put plus or minus 4 over 3. So that this expression represents the equation of both asymptotes, one positive and one negative. All right, and that is it for example 1. All right, guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.